So welcome everyone. Thanks for showing up, everyone. I'm here together with, so my name is Konstantin. I'm here with Priya Danti, and we're gonna present the initiative Climate Change AI. First, of course, we're gonna give a little introduction on what we mean by tackling climate change with machine learning, a bit of overview of the intersections between climate change and machine learning. Then we're gonna talk a bit about our organization too. So, with that introduction, oh my God, sorry. With that introduction being done, I'll hand it to Priya to give kind of first head start on climate change.
All right, thanks, Konstantin. So, as we all know, climate change is unfortunately one of the most pressing issues of our time. We're already starting to see really severe effects from climate change, including storms, droughts, fires, flooding, etc. And the impacts of climate change are unfortunately unevenly spread. In particular, the world's most vulnerable populations tend to feel the worst impacts of climate change. Another sort of exacerbating factor with climate change is the fact that in some sense, some amount of climate change causes more climate change. By which I mean, for instance, when we get some amount of climate change, this results in things like Arctic sea ice melting. This then decreases the reflectivity of the Earth, so it means that we're reflecting less sunlight back into the atmosphere, which then actually accelerates the process of climate change. So this is really, pressing. This is happening now, and it is accelerating. And as a result, the UN Intergovernmental Panel on Climate Change has mentioned that we need to get to net zero greenhouse gas emissions by 2050 in order to avert some of the worst effects of climate change. So net zero meaning that for every unit of carbon dioxide, for example, that we're putting into the atmosphere, we need to be taking 1 unit out. However, unfortunately, emissions are still increasing year after year. There has been a little bit of a blip in this due to COVID, but unfortunately, especially due to policy changes that have been occurring during this time, these emissions are expected to rebound or even increase after we're back open. And so it is more urgent than ever in some sense that we take really rapid and deep actions to address climate change. Now, one challenge with addressing climate change is that emissions come from a lot of different places. So this is a chart from the World Resources Institute that talks about, for instance, what percentage of emissions come from the transportation sector versus the electricity sector versus agriculture, etc. And I'm not necessarily going to dive very specifically into these numbers, though this is kind of a fun chart. If you'd like to impress a friend by having some of these percentages off the top of your head, I would encourage you to come back to this chart. But one thing I'd like to emphasize here is that even though it can seem daunting to tackle climate change, given that it's such a distributed problem, given that there are so many different sectors that cause many different sources of emissions, this also means that there's an opportunity for those who want to tackle climate change in that there are many different places to plug in and actually start having an impact. So when it comes to tackling climate change, there are a couple of ways to think about what you can do. So a lot of people often ask me, actually, is it too late to tackle climate change? We're already seeing the effects of climate change. Is it too late? And one thing I'd like to emphasize is that climate change isn't an on-off switch. There isn't some magical time when all of a sudden it's too late to start addressing climate change. We can, in some sense, control how bad it gets and also make sure that we're equipped to deal with the consequences of the climate change we do experience. And so we tend to think about this in two different categories of action, one of which is mitigation. How do we actually reduce the amount of greenhouse gas emissions that we're putting into the atmosphere, and as a result, reduce the extent to which climate change is occurring? And then adaptation. Given that we are already experiencing some of the consequences of climate change, and that we will continue to do so, how do we build resilience to those consequences around the world? So, of course, so this is a kind of very brief intro to climate change. But of course, today we're at the Algo, a conference focused on machine learning. And so before we get into how machine learning actually ties into this picture of tackling climate change, we're just going to really quickly give a little bit of an overview of what machine learning is and what it's good and bad at. So machine learning broadly is a group of techniques that can automatically extract patterns from data, and usually large amounts of data. And it manifests itself in a couple of different ways. So in particular, Machine learning is very good at scaling human insight. So for example, if I asked Konstantin to, for a particular picture, tell me whether that picture is a dog or a cat, Konstantin could probably do this. If I gave him 1,000,000 pictures to do that for, he probably would never talk to me again. But a machine learning algorithm can definitely scale these kinds of human insights by finding patterns in large amounts of data. Similarly, machine learning is good at optimizing complex systems in a variety of circumstances, at sort of generating usable insights or data from streams of data that might not be as useful. So for instance, there are a lot of applications that use satellite imagery, large streams of data that we have available, to actually produce actionable insights that we can use for climate change. And Konstantin will talk a little bit about this later on in the talk. And then finally, machine learning has recently started to better integrate with other kinds of methods. So things like physical models that we might have about the weather or energy systems, et cetera, so that you can, in some sense, combine the power of data-driven methods with the power of these other methods. That said, while machine learning is a really, really powerful tool, it does definitely have its limitations. In particular, machine learning relies on data. And so if the data is bad or limited or biased in some way, then the outputs of your machine learning model will similarly be limited. And so this is characterized by the garbage in, garbage out aphorism. And machine learning, importantly, as a result of that and many other factors, is not objective. I've definitely had people come to me and say, can I write a machine learning algorithm or a reinforcement learning algorithm more specifically to actually optimize everything in society and come up with the best climate policies? And the answer to that question is resoundingly no. In some sense, climate change requires a lot of value judgments about, where exactly do we reduce emissions? How do we do that? And in some sense, who are the winners and losers going to be? There are a lot of value judgments here, and machine learning can't make those for us. And in particular, the way we the data we give to machine learning algorithms, but also the way we choose to design them, how we choose to use them. Machine learning tends to just amplify the systems within which it's employed. And so making sure that those systems are actually, pointing us in the direction that we actually want to go is extremely important for the success of machine learning algorithms in this area. Finally, machine learning, as it analyzes patterns in data, it tends to assume that those patterns persist in settings where it's going to be used. And so there are some cases where machine learning has difficulty when we see patterns changing over time. For instance, if we think about long-term weather forecasts, well, the weather is going to shift because of climate change. So machine learning models that are trained on current weather information might not be able to cope with future. And then finally, machine learning methods like statistical methods in general provide correlation, not causation, though there are some research directions in causal machine learning. Okay, so how do these two things tie together? Machine learning, climate change. So about 1.5 years ago, a group of us came together to write a paper that tried to answer this question called Tackling Climate Change with Machine Learning. In particular, some of us were coming from a machine learning background and sort of trying to think about, well, we know there are some ways in which machine learning has started to be impactful, particularly in the electricity sector. There's been some work in this area for a number of years. But are there other sectors, for example, in which machine learning is potentially impactful in helping us to tackle climate change? And simultaneously, there were a number of people from the climate change community that were starting to see large streams of data, for example, from satellite imagery, and wondering, can we use insights from this data to actually inform the way we address climate change and also climate policy? So a bunch of us basically came together to try to answer this question of how exactly does machine learning plug in? And so Konstantin is going to start by giving a bit of an overview of some of what's covered in the paper.
Thank you, Priya. So the CCI paper is broadly split into 3 parts. With the first part, 2 parts referring to what Priya mentioned earlier, mitigation and adaptation. So again, mitigation is concerned with all sorts of efforts that aim at reducing carbon emissions. And obviously carbon emissions come from lots of different areas in our world. Obviously, one of the biggest ones is electricity systems. So think about coal plants that produce energy, but produce tons of emissions. Transportation, from cars to air traffic to the shipping routes in our seas, they all have lots of emissions. Cruise liners too. Buildings, and especially like agglomerations of buildings, so cities, are a big source of carbon emissions. So is heavy industry. For instance, the fertilizer industry is one of the biggest producers of carbon emissions. farms and forests as well. So forests obviously take in lots of carbon dioxide, but as more and more forests disappear to make a place for farmland, this kind of beneficial source of capturing carbon falls away. And on the other hand, increasing demand for instance, meat leads to more cattle production, and cattle is a big source of carbon emission too. Mitigation is also concerned, of course, with the removal of carbon dioxide, and that starts from planting trees to more advanced methods of capturing carbon that is in our atmosphere. So that is mitigation approaches. Adaptation approaches, as Priya mentioned, deal more with accepting that climate is changing and that this will have, in part, really gruesome consequences for certain populations. So how can we adapt to that? And one thing in that sense is that it will be increasingly more important to have very precise climate predictions. And machine learning can help with making good predictions. So machine learning can be leveraged for improving our climate models. We are also looking into the societal impact. As Priya mentioned before, climate change will not hit everyone the same. Already really poor off people are hit the hardest by climate change in areas like Pacific Islands or so that are only a few feet over sea level. So the societal impacts are very important to address too. And adaptation also deals with issues such as solar geoengineering, which we're not going to go much in this talk at least. The paper then has the last big part is focused on tools for action. So this includes individual action, so action taken by individuals. It includes policy and all sorts of AI-supported policy making, and then issues such as education and finance. So in our presentation today, we want to focus a bit on the areas that Priya and I do research on ourselves. So that will be electricity systems, transportation in cities, so urban transportation. We'll talk a bit about land use and also about the societal impacts. And I will get started with my research in the beginning. So the first thing I want to talk about is land use. So land use is basically concerned with all sorts of all sorts of use of the earth we have, right? So whether that is built environment like streets or buildings, or whether that is farmland, or whether that's kind of a wild environment that is not touched by humans. And so understanding land use is crucially important for running simulations and for driving policy, data-driven policy. And one of the most important tools for this is remote sensing. So that is using data captured by satellites or drones, aerial imagery, to perform all sorts of tasks, be that object detection. There was an amazing big paper coming out in Nature, I think, this month that counted all trees in sub-Saharan Africa using satellite images. There's tasks like semantic segmentation, so when you want to find out, for instance, the building height or something like that. For spatial temporal forecasting, so that relates again a bit to climate models, or super resolution. And super resolution is something that I want to talk about first. I'll also talk about a bit about the data underlying it. So one of the research projects I'm working on is helping neural networks to learn spatial patterns. So spatial data is a bit different from your everyday data in that it's not particularly great or easy to model it, so make predictions with spatial data. And that is because if you think about the very simple linear regression framework, one of the key assumptions for linear regression is that your data is independent. And that is not the case for spatial data often, because spatial data exhibits spatial patterns. So that means that what's a good example to say that? For instance, if you look at the price of a house, your best guess for the price of that house might just be looking at the price of the house next to it. So you have something that we call a spatial autocorrelation. So where a value at observation A is very dependent on the values around it. And so neural networks are not necessarily able or really great at capturing these dependencies. So one project, for instance, that I'm working on is helping them to make this better by using spatial autoregressive embeddings as an auxiliary task in a multitask neural network. When we learn both at the same time, so the original data and its spatial embedding, you can get to you can improve the learning in your neural network and get to better output. And the task that I want to highlight here is super resolution. So that is basically upscaling an image, right? If you have an image and it's like 16 to 16 pixels, and you want to get a higher resolution of that, let's say 64 to 64 pixels, that is something that neural networks can do and learn given you have good training data. And what we found in the study that I'm highlighting here is that if you let your neural network not only try to do that super resolution on its own, but also help out with providing the spatial embeddings, you actually get slightly improved results. And this has applications in all sorts of remote sensing research, from like the data that I'm using here in these example images is digital elevation maps, so finding the elevation at each pixel, but it also has applications to underwater seabed data or to tree canopy data. The second land use project I want to highlight is a recently published one of mine, and that is goes a bit away from the methods and goes more into the data that we use. So one very important task that increasingly uses machine learning is estimating the population of informal settlements. So informal settlements are slums, but we try to stay away from that terminology a bit because it's not really scientific, and informal settlement is just a much better way to describe these settlements that are often unstructured. And estimating the population in these informal settlements is very hard, and often the estimates are really bad. And this is really a problem when it comes to disaster relief. So imagine a flood hitting a very poor area in a very poor informal settlement in Lagos, Nigeria. It is very hard for help organizations to efficiently allocate resources to help. And in order to improve that, it's important to have good estimates of how many people live in that area. Now, what we could do is, of course, we could just take a satellite image and count every single house and get an estimate from that. However, we won't get a very good model from that. And so in order for, and this is reiterating a bit of what Priya said earlier, in order to actually build good AI systems, we need to provide the AI system with good database that it can learn from. And so far, there are not great ground truth data for informal settlements available. So this project here uses data from a project at University of Warwick that's still ongoing and expanding, that has a very participatory approach to getting this ground truth data. And we believe this approach is very important because it is fair, it includes the local population, it is democratic, the data is going to be open source, and it is not kind of the European researchers coming into Africa and mapping things. Instead, it is us learning from the locals and learning about their home and taking all that local information into account in order to create data that is a data set that is equitable. How we call it equitable ground truth. And then you can build models based on that. And ideally, should your data be as good as you want to make it, these models would generalize well into other unseen informal settlements. So these are two kind of land use machine learning projects that I've been working on. I want to close my case studies with a different application, and that is transportation systems. So with cities growing more and more, and also being one of the biggest sources of emissions, there is a crucial need for optimizing urban transportation. And in recent years, we've seen a big shift from kind of personal car transportation in cities towards more public transport, shared solutions, and also active travel like biking. And so if you think about the car sharing system, for instance, it is really tricky to optimize those, right? So where do you provide your shared cars? Like, what is the best spot? is the spot where you provide a car always the best one, or is it like great in the morning when people commute in the city, but then in the afternoon no one will want to pick cars up from the suburbs anymore because everyone is in the city? So how do you balance out shared mobility systems? And this is where machine learning can come into place and be a especially helpful tool. So we're talking about optimization here. So how can we optimize a complex urban system with many different layers and many spatial temporal dependencies? And this is an older paper of mine, actually work that came out of my bachelor thesis. But basically, we developed a system that uses point of interest data, so that points of interest are can be anything from a restaurant to a park to a hospital, to estimate car sharing demand at a given point in time. And the particularly interesting thing in that project, I believe, is that we found this to be rather well generalizable. So if you imagine you train your algorithm to predict the car sharing demand in Amsterdam, we were actually able to use those regression coefficients and use them on a different city, so on Berlin, and get really good results. So this shows that there's kind of shared patterns between the two cities that then can be leveraged to optimize your systems even more, and to learn kind of a global pattern of this demand. And with that, I will give it back to Priya for her case studies.
Awesome, thanks, Konstantin. So far we've heard about a couple of different case studies in areas including, disaster relief, transportation, land use, using techniques such as remote sensing. So I'm now going to try to highlight a slightly different set of applications in the electricity sector, using techniques from time series analysis and reinforcement learning, just to give a bit of a kind of, again, overview of a couple of different kinds of techniques. So one of these applications that we care a lot about is forecasting electricity supply and demand. So on the electric power grid, we have this really challenging problem of needing to balance the power grid at every single moment. So specifically, the amount of power, previous slide, please. Thanks. So on the, for every moment, we have some amount of power that's being produced, for example, from solar panels and wind farms. And we also have some amount of power that's being consumed, for instance, if I turn on the lights or the air conditioning in my building. And the amount of power that's put into the power grid at any given time and the amount of power that's consumed have to be exactly equal always. And so having foresight or estimates of how much power supply there's going to be or how much power demand there's going to be can help us address this scheduling problem. Similarly, having longer term forecasts of electricity supply and demand can help us figure out how we are going to actually transform the infrastructure on power systems, things like building new renewable energy infrastructure or building new lines to actually transport electricity from one place to another. So this is a really multifaceted problem. It has a lot of moving parts, from engineering to policy making, etc. But machine learning can plug in by helping provide short and medium term forecasts of electricity supply and demand. And this is by taking in things like historical data about the weather or the outputs of weather forecasting models like numerical weather prediction models, and also things like images and video data. So for example, there have been a lot of recent applications that have looked at, if you put a camera that's facing upwards next to a solar panel, can you take a look at how the clouds are evolving over time and understand basically how that'll affect the output of your solar panel? So machine learning basically has been used in a lot of different ways to kind of combine very heterogeneous different kinds of data in order to produce these forecasts. And this is a really active area, and there are a lot of important considerations inherent in making sure that this actually works well in practice. So one of those is one area of work, which I'll touch upon a little bit in terms of my own work, is how do you actually incorporate knowledge about the power system, the physics of the power system, and also the way in which the power system is optimized into your forecasting algorithms, so that these forecasts in some sense can help us make better decisions, or explicitly trying to help us make better decisions. There have also been some recent work in how we make sure that our models actually are able to characterize the uncertainty of our forecasts properly. So for example, tell us if I'm very certain that this is the amount of solar power that'll be produced tomorrow versus if I'm less certain, maybe that has different implications for how the power grid is actually optimized. And for similar reasons, there's been a lot of focus on making forecasts interpretable. So I'm going to just go very briefly into my own work in this area, which is again in that first aspect of incorporating system physics and goals. So in particular, in my work, I look at the following problem. When we create forecasts, we usually optimize these forecasts to be as accurate as possible. So for instance, if I have a certain amount of power demand tomorrow, and I predict an amount of power demand that is similar to that, then my forecast is good. And then the forecast of, for example, electricity demand is fed into some optimization algorithm that's used to actually schedule power on the power grid. And then the results of that algorithm are used to actually tell power generators, hey, this is how you should adjust your power output. And there are lots of, engineering and physics constraints that govern how that goes. For instance, a power generator can only change its generation by a natural gas or nuclear generator, for example, can only change its power output by so much from one time to another due to physical constraints. And I argue that this way of doing things is pretty normal, but is actually limited. So in particular, I mentioned that forecasts generally just try to improve the accuracy of their predictions, but different kinds of mistakes actually have very different implications on the power grid. For instance, if I predict that there's going to be more electricity demand than there actually is, then an electricity system operator might actually schedule too much power generation. And when we actually see the real amount of demand, they might go, oh no, and have to waste some of that power generation. So that's sort of resulting in wasted emissions and power costs. On the other hand, though, if we forecast the demand will be too low, so if our forecast is too low, maybe this means that the electricity system operator actually gets too little power generation scheduled onto the power system. And this is worse. It can be a lot harder to sort of make up that deficit in power. It can result in really large costs. It can result in blackouts, et cetera, et cetera. And so when we just try to optimize our forecasts for accuracy, we're often missing out on a lot of these real world factors that actually govern how effective they'll actually be at helping us to reduce emissions or to reduce costs. And so briefly, what I actually look at in addressing this problem is, instead of creating forecasts that are optimized for accuracy, actually creating forecasts that explicitly optimize for the quality of the decision that's made on their basis. So a forecasting model that says, if I make a prediction, what is the decision that the electricity system operator is going to make on that basis? And then what is the cost of that actual decision when it operates on the real world? And we do this by basically incorporating power system scheduling models into our forecasting algorithm, which is based on deep learning. And for those who are sort of into the area of deep learning, next please, for a neural network to work, every single component of that neural network has to be differentiable. And so we sort of get into this challenge of how do we actually differentiate through power system optimization algorithms that are in these neural networks. And we do this using optimization theory. So if you didn't follow that last part, no problem at all. But the general upshot here is that in the specific work, we look at how do you actually make sure that your electricity demand forecasts are aware of the ways in which they'll be used and are able to compensate for the limitations of the ways in which they'll be used. And more broadly, the takeaway is, as we sort of do machine learning work in the context of climate change applications, we really want to be thinking about, what is the larger workflow in which this will be used, and as a result, how can we actually change the way in which we do machine learning to actually better service that application? So that was one application of time series analysis to electricity systems. So as I mentioned, in electricity systems, we do need to be able to optimize the power grid at every given moment to accommodate renewables. And we also want to make sure that this optimization is robust. So this gets to another kind of challenge of how do we actually do this power system optimization well? And a problem here is that a lot of our existing power system optimization algorithms are really large and really slow. And this means that we need to figure out ways to speed up energy systems optimization, which is something that machine learning has been used for. So specifically, machine learning has been used to both try to speed up some of these centralized power system optimization models, for example, by trying to figure out if you can reduce the complexity of these models using data-driven methods. And there have also been a lot of methods to actually try to decentralize power system optimization using things like reinforcement learning or techniques from control theory to try to control solar power inverters or smart HVAC or smart industrial loads on the power grid in order to then balance the power grid in a more dynamic and distributed manner. So I'm going to talk a little bit about that second part in my own work, which is enabling decentralized optimization. And as I mentioned, a key challenge here is making sure that the power system stays robust as you do all of these things. And so, yeah, so the question I try to address is basically, how do you manage this increasingly complex power system with lots of different devices and lots of different objectives, while still making sure that the power system is not going to black out, that you're still satisfying some of the physical constraints on the power grid? And so we use a deep learning approach to actually address this. So deep learning approaches are notoriously terrible at enforcing hard constraints on the power grid or in other settings. And how you'd usually use a deep network-based approach to control a system is you would look at the current state of your system, you would put that state into your neural network, and then you would let that neural network try to predict maybe some kind of action that you should take to control the system based on that state. But as I said, this kind of is notorious in neural networks, that these outputs, these actions that it suggests are not really going to satisfy any guarantees. And as a result, there's sort of no guarantee that your system is actually going to stay stable, which is really a deal breaker for electricity systems applications. So what we do, next please, is actually bring in guarantees from control theory. So control theory being a field that deals with how you actually, manage like batteries and solar inverters, et cetera, on power grids and in other systems, but actually comes with guarantees as to how you would do this in a way that's robust. So we actually bring in various guarantees from control theory in order to modify the policy or the action that is output by our neural network in a way that sort of ensures that that output will be robust. And so this sort of illustrates another theme generally in climate change work, which is that there are lots of places in which we have a lot of data in which algorithmic systems are needed to make increasingly complex decisions, and where existing techniques, for example, are maybe really slow or really difficult to scale. And it's often very tempting, kind of the first brush attempt that a lot of machine learning practitioners take is to just say, well, let me bring in a machine learning technique, let me throw it onto some data and it should work. And in a lot of cases, that isn't the case. Throwing out the existing knowledge we have about our system is not usually going to be the right move. And so kind of a big theme in a lot of climate change work is how do you actually integrate insights from climate modeling or from electricity systems or from transportation systems that we already have about their physics and engineering, along with machine learning methods and data-driven methods. Okay, so that was sort of a little bit of a deeper dive into some of the areas that Konstantin and I are working on, which are meant to sort of illustrate that there are really very many different ways in which machine learning actually can plug into the climate change picture. And so in our broader paper, we sort of identify various recurring themes for how this actually happens. So you saw an example of forecasting, for example, so forecasting electricity supply and demand, but there are also applications to forecast extreme events using climate models and machine learning models in order to help, for example, city planners adapt to disasters, and also forecasting of things like carbon prices and markets. There are a lot of applications in both data mining and remote sensing where you're taking information such as satellite imagery or Twitter feeds, et cetera, and using that to get some kind of information about disaster response or urban planning. There are some projects that are trying to map global greenhouse gas emissions using satellite imagery. And in all three of these cases with forecasting, data mining, and remote sensing, these are all ways in which basically machine learning helps us get insight. But I'm going to emphasize that in all three of these cases, that insight has to be followed by action in order for there to be kind of an impact. And so this is something to keep in mind if you're working in one of these areas. Another key theme is that machine learning can help with fundamental science and engineering problems that we face as we do climate change innovation or as we optimize real world systems. So I talked about, for example, applications to try to accelerate the way in which we do energy system management. There are also a lot of applications in climate science where we have climate models that are really large and slow, where you can use machine learning to help reduce aspects of these. And there are lots of applications also in sort of the development of next generation technologies like batteries or solar panels or even nuclear fusion, where, for example, practitioners may have tried a bunch of different experiments to get these technologies to work, and may want to understand what is the best next experiment that I can try that is most likely to succeed. And so machine learning has been used to basically look at previous sets of experiments and then actually predict what experiments are most likely to be fruitful next. So these are basically applications, again, where we can sort of use machine learning, previous slide still, thank you, to help with the process of science and engineering. And then finally, there are a lot of applications where we can actually then use machine learning to optimize real world systems or to try to figure out how to make these systems more efficient. And these are applications like scaling up land-friendly agricultural practices that can help us reduce emissions, optimizing heating and cooling systems, finding leaks in natural gas pipelines. Natural gas is the same as methane, which is a really, really potent greenhouse gas. And so there are a lot of scenarios in which, as we transport natural gas to electricity generators, these pipelines leak methane, which is really bad for the climate. So there are lots of applications of machine learning to actually try to detect those leaks, for example. And so in general, this idea of optimizing systems becomes very important. And I'll emphasize here that a lot of these applications in the real world are not necessarily sexy, that it's really tempting to want to do something that's really flashy with machine learning, but really sometimes a lot of these more kind of less flashy applications are actually going to be really impactful. Yeah. So a couple of important considerations. So machine learning, importantly, is not a silver bullet. So we've talked a lot about applications where machine learning is applicable, but it is not applicable everywhere. So for example, there are a lot of applications in policy, for example, where people expect machine learning to help make a decision about how policy is going to work. That's not necessarily always going to be the case. Where machine learning is applicable, it's only one part of the strategy. So for example, there are a lot of applications to try to manage smart appliances within buildings, but in order for those to be impactful, you have to insulate the buildings first. So it's going to be really important. And in general, machine learning is, since it's only one part of a larger picture in any of these cases, it's really important to understand the systems context of your application. So for example, if I work on machine learning for precision agriculture, trying to scale agriculture, that on the one hand can help us manage land more in a way that's sort of friendlier and sequesters carbon dioxide emissions better. But on the other hand, sometimes making agricultural processes more efficient can cause them to be used more, which can increase emissions. Or machine learning algorithms are often more accessible to those with power than those without. And so precision agriculture approaches, for example, would be more likely to benefit large farmers than small farmers, which might exacerbate those gaps. And so there are lots of considerations to think about when using machine learning in these contexts to make sure that you're actually both solving a problem that needs to be solved, and that the life cycle impacts, the longer term impacts and the system impacts of that application are actually what you want. And since this is often a lot to keep in mind, you really need to be surrounding yourself with people with very different perspectives and with very different sets of expertise on these different issues. And as a result, work needs to be driven by collaborations with other experts, also the end users of any particular application, and also people who may not be directly in the loop, but who may be affected by a particular application. Definitely there's a huge amount of opportunity in using machine learning for climate change, but there's also a huge amount of responsibility. And so keeping these things in mind is going to be really important for those working in this area.
All right. So what Priya just outlined the considerations that we have to take, and based on those considerations, CCI has developed a bit of a roadmap for action based on this. So we believe there's like 4 key components to this, and the first one being to learn. And with learning, we mean all sorts of learning that is applicable to you and your situation. But there's many different ways to get involved. So one goal of climate change AI is providing lots of resources for learning about the intersection of climate change and machine learning. But obviously, it's not just us. There's plenty of other organizations that also try to provide education. There is more and more actual university programs that are aimed at this intersection of AI and machine learning. And I will mention one of them later. That is actually at UCL. The second kind of pillar is collaboration. And we believe that collaboration is so important because, again, climate change is not like a single dimensional issue. There's plenty of different perspectives to it. There's many different disciplines that have to work together in order to come up with something actionable. Priya just mentioned that many of these kind of data-driven systems that we presented are just something that will, in the end, produce a prediction or so. This is not something that is a direct action, right? So in the end, we need to provide understandable, intelligent systems that can provide decision makers with the information they need to make a good decision. And yeah, so collaboration with different perspectives, gaining insight is extremely important. And in the light of that, listening is what we believe is key. And that is that you will always come to an issue as broad as climate change from your own perspective. And we believe that it is really key to listen to collaborators and to listen to other stakeholders and understand what they're saying. So we're saying here, be humble, and yeah, with that we really mean, like, try to kind of emphasize with other people's perspective on these issues, and try to listen to people who are maybe directly affected by climate change or who are working in the industry and have a different perspective on things. And lastly, all these three previous points lead into the deployment of effective policy projects, and keeping the end goals in mind, staying focused is really key to having projects that are successful and drive impact in the space. And from kind of these more abstract guidelines to more concrete advice that we can give. So in general, like I just said, check out CCI resources. We have an amazing forum full of like-minded people who are chatting about, papers they've read, who chat about organizing study groups, who chat about projects they want to do. We have a newsletter. We have tutorials both for technical and non-technical people, giving introductions to climate change and machine learning. We are working on a wiki right now, like big climate change AI Wikipedia that is coming soon. And obviously we're organizing lots of talks like this, but we're also organizing workshops at big academic conferences and at non-academic conferences, more industry-focused events. And at these events, we usually record talks and have a library of a lot of amazing speakers from whom you can learn. So for instance, you can check out our YouTube channel, but our talks are also on other YouTube channels. One that I would particularly recommend is the TEDx that happened recently. I don't know if the videos are up for that yet, but they should be soon. Also plug into the UK climate change and machine learning ecosystem. We have a slide just below this one that I will go into that presents that a bit more. For students, we really recommend you reach out, you're proactive. There are lots of people who are working in this space. Reach out to them as potential mentors and collaborators. Write them an email, familiarize yourself with their work before, and then reach out. And the kind of the worst thing that's going to happen is that these people are going to say they don't have time or they're not going to reply. But this kind of proactiveness is super important. Same goes for multidisciplinarity. So Priya and I have both either taken classes outside of our field, or my background is even in economics, and then coming into computer science. And we both think that this kind of interdisciplinary approach gives you tons of new perspectives and makes you think about problems from different angles at the same time. For the professionals here, there's plenty of communities and meetings that you can join. Meetups in London is a big city. There are lots of interest groups. There is always municipal interest groups and public engagement groups, for instance, focused on local public transportation and so on. And that we really recommend you to join. And then also as a industry person, leverage your network. Maybe you can drive change from within your company. Maybe find like-minded people in your company that are also interested in climate, and together you can organize in your company. Also leverage people who are not in your company but who work on stuff that really interests you. You can brainstorm with them, you can exchange with them, and maybe that can lead you on a path that helps. Just to briefly mention the UK climate change and ecosystem that I was talking about. So at UCL, there's actually a Masters of Energy Systems and Data Analytics. Check that program out if you're currently an undergrad student and are interested in a master's. The Alan Turing Institute has plenty of research themes that touch on more indirectly or directly on climate change. The Alan Turing Institute also has plenty of videos online that you can use as educational resource. Open Climate Fix is founded by an ex-DeepMind employee who dedicated this project to open sourcing code on I think a solar energy forecasting. So you can contribute to some nice open source code base there. And lastly, the International Center for AI, Energy and Climate is a very new center based in the UK that tries to bridge the gap between academia and the startup economy. So basically a center that tries to support young entrepreneurs coming out of academia. Lastly, because we're running a bit over time and I want to leave some space for questions, to quickly sum up, so we at Climate Change AI, we're an initiative that wants to facilitate, so we're mostly a facilitator of work at the intersection of climate change and machine learning. We are a completely volunteer-run team from around the world. We're currently growing in the process of getting new members on. We have an amazing board of advisors that kind of keep our vision focused, including people like Demis Hassabis, who you might know, he founded DeepMind, that's just based next to UCL in London, and Felix Kreuzig, who was a lead author on the IPCC report that Priya was mentioning earlier. In the most recent future, we have a workshop at NeurIPS 2020, the biggest machine learning conference. It's on December 11th. Especially if you're a student, this could be attractive for you because conference tickets are only $25. There will be over 90 accepted papers and posters you can check out at the workshop, and plenty of keynote speakers, plus obviously the program from all the other workshops and the main conference. This is our CCI forum that I mentioned earlier. Definitely check that out. It's very active at the moment, so you'll find lots of like-minded people to collaborate with. And lastly, our newsletter is a monthly newsletter with jobs, funding opportunities, interesting events that are happening that you can register for, and projects. So check our newsletter out. With that, we're pretty much done, and we can go over to questions. And I think we have a lot in the chat. Priya, maybe can you read one of the questions, because I will try to stay in this slide so we can go back to a slide if needed.
For sure. So I'm going to group two questions, which I think, Konstantin, you're the best to answer. So
right.
Agricultural production generates a lot of greenhouse gases that contribute to climate change. So how can we use artificial intelligence in agriculture applications? And then also, how can AI help in the classification of dynamic images of groups of sensing? I'll let you start with both of those.
Right. So the first thing I want to say there is I want to refer you to a person, Catherine Nakalembe. She's the lead of NASA Harvest, which is NASA's agricultural program. She also gave a talk recently at the climate change AI TEDx. So you should be able to find some talks of her online, because she does exactly that with a focus on Africa, right? So as Priya mentioned before, precision agriculture is basically optimizing everything around, from fertilization to kind of predicting certain temperature shifts that might require you to cover up certain crops. So this mostly benefits large farmers. What I want to say about agriculture and AI is Catherine Nakalembe's work, which is focused on small farmers, so like only farmers who are self-sufficient, so kind of only produce stuff for themselves. And Catherine has collaborated with lots of them and looked into kind of these kind of small farmers' needs, and with the help of drones. So not that every farmer needs a drone, obviously not every farmer around the world can afford a drone, but with the help of drones, she's kind of mapped the local farmland And based on that, and some simple machine learning, created tools for very simply and one-time decision support for these farmers. So stuff like that is something that I would definitely recommend you look into.
Awesome. And Konstantin, do you mind if I try to fly through a couple of the next ones?
Yes,
so
sure.
we can try to get to everyone's. Okay. So there was one question about many signs of climate change that we're seeing. So glacial area disappearing, extreme temperatures, deforestation, etc. So do we have intuition about which threats are the most pressing ones we need to deal with? So from a mitigation perspective, in some sense, I would say dealing with reducing the amount of greenhouse gas emissions will sort of tackle all of these things simultaneously. In terms of adaptation to these, honestly, there are a lot of value judgments here. There are, of course, many different people in many different locations across the globe who will be facing different impacts. And so I wouldn't want to necessarily pick winners and losers in some sense in terms of which are the most pressing to deal with. But I would definitely say if you have ties to or collaborators in a particular geographic area, or feel that there are geographic areas that don't necessarily get as much attention and that will need climate change adaptation capacity, that would be one way to sort of channel your efforts here. Also, Konstantin, if you disagree with anything I say at any point, feel free to jump in and breeze through. There was a question about the effectiveness of solar and wind farms due to batteries, and the fact that these plants are often offset by building more fossil fuel plants. So talking about this and sort of the life cycle impacts of solar PV in terms of rare earth metal mining, et cetera, et cetera. And is nuclear just not better overall? So there are a lot of, so many of you may have seen a documentary called Planet of the Humans, and I'm going to start by saying that this documentary is actually super, super misleading. So the solar and wind farms, for example, their variations in their output does need to be balanced by either energy storage like batteries or natural gas power plants. But in general, we don't tend to build new natural gas power plants to offset intermittency from solar and wind farms. Actually, our existing plants can more than deal with this. There happens to be some correlation between the solar panel boom and the natural gas boom because of both aggressive action to increase solar deployments, for example, in Germany, and at the same time, just sort of falling natural gas prices around the world that caused a natural gas boom. But these things are actually not correlated with each other. So that's just one thing I want to clear up. But to sort of get to the general spirit of the question, yes, I think there are always trade-offs when we think about, if we're going to use a lot of batteries and solar panels, then there's going to be a lot of, metals that are mined for that. People are trying to think of alternatives and sort of better ways in which we can do this. And yeah, I think ignoring these life cycle effects doesn't necessarily make sense, but largely solar, wind, and nuclear, are going to be better than dealing with fossil fuel power plants, which, for example, the pollution from those kills like thousands of people a year. But in the nuclear versus solar versus wind debate, we will need a mix of all of these sources. There are definitely people who have different opinions about the various aspects of these, but in my opinion, we will need kind of a combination of all of them. Another question was, are there any applications in mechanical system or component design or feasibility studies for fuels? So yes, there are lots of applications of machine learning to basically optimize like factory processes or to try to search over different kinds of potential fuels that could be feasible for synthesis and experimentation to see if they'll work. So yeah, definitely a lot of applications there. On the question of how much focus is there on minimizing the impact of machine learning and its applications, like their own energy use, both in our group and in the field in general. So this is, again, one place I want to disambiguate. So there are lots of different machine learning algorithms, some of which are definitely super emissions intensive. For example, there was a paper showing that kind of training and building one of the largest language models from scratch can have emissions equivalent to like the life cycle emissions of a car. But on the other hand, a lot of models that are used in climate change areas are actually really small. So most of the models that I actually run in my own research run on my laptop. And so the kind of focus in our group has been on basically trying to encourage people to really think about all of these things. So think about when I'm using machine learning for a particular application, is it going to have, I mean, what are the impacts it's going to have on emissions? Is my model, like, how can I make my model as efficient as possible? In a lot of cases, in a lot of the applications that we've talked about, the sort of emissions trade-off does work out such that the emissions associated with the machine learning model definitely do kind of pay back more over in emissions benefits for the application. But there are lots of cases in which that may not be true. And so there's also been a lot of research in the machine learning community as a whole in terms of how do you create more energy efficient machine learning algorithms and how do you benchmark the uses of these. I think the next question, Konstantin, you're more likely to get to, or are we over already?
I think we can do one more. Also, I quickly wanted to add, I think it was Yaringal from Oxford. He actually suggested once that kind of the emissions of a model training process is used as a benchmark metric. So there are thoughts about this in the machine learning community. I think already, like, there's big communities who work on kind of tiny ML, so small models, network pruning, and so on. There's communities that look into, of course, a lot into efficiency of training. So indirectly, I think there's a lot being done already, but obviously it's an important topic. Yes, that next question, Priya, which one did you mean?
Yeah, so how can AI help in LiDAR imaging without underestimating and overestimating in dense forests like Amazon rainforest? Yeah.
I don't think it can yet. I don't think we're far enough, like, because a forest is such a homogeneous environment. To the best of my knowledge, we are not at the point where we could be really good with that. I also don't know if there's enough projects. So when I see LiDAR papers, they're usually in cities and so on, or like cars. But I've not seen all too many that really work with like forest LiDAR data. So I think that's a really cool challenge to work on, actually. I imagine it's a really hard one though. But sorry, that's a disappointing answer.
So yeah, thank you everyone for coming. Sorry to rush through those questions. Just wanted to make sure we got to everybody. Yeah, so please feel free to check out the resources and plug into the community at Climate Change AI, and we hope to see you soon.
Bye-bye. I'll tell Adriano to come and then he'll take care of things.
Great.
You're on the thing, man. Get off the screen, man.
Okay. I joined in the end. I just want to say a few things. Thanks, Priya, very much. We didn't have the chance to really connect, but I'm very glad for you to have joined. I'm going to upload the video on the UCL AI Center YouTube channel. So, and of course, thanks, Tino. You're my brother. So I'm really glad for you to organize that. Thank you both very much.
Thank you for organizing.
Yes.
Thanks. Bye-bye, guys. Take care.
Bye-bye.